Okay, can I start?
Give me a second.
Oh, I see.
Yeah, you kind of start now, Jenny.
Ah, sure. Thank you. Can anyone see my screen?
Mm-hmm.
Yes. Okay, great. Hi, everyone. I'm Xin. I'm a postdoc of this group. So today my tutorial is about focused ion beam. And so first, before I jump to this topic, I would like to give my self-introduction. So I was born in Xuzhou, a small town in the eastern part of China. And then I went to Nanjing University to study physics. I focused on the optics actually in my undergrad, which is about the light matter interaction, optical force, something. And then I went to University of Hong Kong as a visiting student and studying, actually learned some MD simulation. Later that year, I joined a PhD program in Northwestern, and where I totally changed my research field. So I met Sosina there, and I studied the solid state ionics in the energy storage materials, which are used for fuel cells. After I graduated, I would like to continue my research in this big field, not exactly same but related. So I joined the Chu group, and right now I'm studying the solid state batteries. So hopefully I can use my expertise, which I learned at Northwestern, to gain some understanding in this battery field. Okay, back to the tutorial. Today my tutorial only have two sections, and the first is what is FIB, focused ion beam, and second, the FIB capabilities. So actually there was a funny time when I was a first year PhD student. So I remember one day when I talked to my roommate, said, I will do FIB tonight. And my roommate was quite confused, and he said that you are an international student. What? So then I realized that he thought I was doing some FBI work. So actually, it took me some time to describe what I'm going to do about the FIB. So in the future, I just use the FIB rather than FIB, just to avoid confusion. So here I spent around 3 years to 4 years working on FIB to do some nano fabrication, local measurement at Northwestern. So what is FIB? So FIB, FIB is is short for focused ion beam, and the main body or the main part of FIB is just SEM. They have a SEM. So this is the Helios, the typical FIB manufactured by Helios. It has a vacuum chamber, and this is the electron column, and it's usually a electron beam parameters 30 kV to roughly below 1 kV. The current you can adjust from nanoamp to picoamp. For FIB, usually I have two set of parameters you can use for imaging. If you are really interested in the fine surface features, you may want to go lower voltage, lower current, because it can give you a finer surface resolution. But usually people will be working on the 5 kV and nanoamp current because it has a higher signal to noise ratio, which means you can easily align the beam and do the adjustment quite easily. So there is the unique feature which is quite different from SEM. This is an ion column. This is the 52 degrees away from the electron beam. You can see here. So the ion column or ion source use the liquid gallium metal here, and the accelerating voltage ranges from 30 kV to around 2 kV. So unlike electron beam, so people usually image sample surface at higher voltage, like 30 kV, because at this high voltage, you can have a good image quality of fine surface resolution. But if you use like 5 kV or 2 kV, you will have very bad quality, which means the noise is very high. You cannot focus well. And usually at 2 kV low voltage, people use this beam at a low voltage to just polish the sample surface and do some etching work rather than image. So I will get to this topic later about the etching by FIB. And there is another feature, which is there is an Omni probe installed in FIB. So Omni probe is basically a custom probe with tip size less than 1 microns. So which you can use this probe to transfer samples locally and also do some interesting things, which I will also discuss later. So in this chamber, you can choose the sample stage to let your sample face to the electron beam or ion beam. In this way, you can just do some change the mode between the electron and the ion beam mode. And during imaging, etching, or deposition, I will also talk about later. So next is the FIB capabilities. So the basic part of the FIB is it's still SEM. It can do almost anything you can do with SEM, and you can do the imaging. You can do also EDEX. Also, you can do the electron backscatter diffraction, which is generally used to detect the grain orientation if your material is polycrystalline. But since the FIB has ion column, they can do much more things than regular SEM. Like you can do etching, locally etching, local deposition, also Micron Manipulation of your samples by using the Omni probe. So first, I would like to talk about etching. So the mechanism of etching is pretty straightforward. So it's a gallium beam, liquid gallium beam, accelerated with up to high voltage. And when the gallium beam image to a sample surface, it kind of just it will if the energy of the kinetic energy of the gallium exceeds is larger than the surface binding energy, it will cause the sputtering effect on your sample. And during the etching, you can also flow some gas to help etching. And this is not very normal, but some group or some FIB has this function. They have nozzle to flow some precursor to help etching to make the etching more efficient. And they also charge neutralization function, which can flow some electrons to the surface. Just if your sample is not very conductive, when the etching goes deep, it may have some charging issue. So this electron will neutralize this charging problem and make your image got improved. Image quality got improved. So I will just show some examples of etching. So first, you can use the gallium to do a line mill. For example, you can cut a very deep trench with only nanometer scale but micron deep. And you can use this. This is the kind of basic step you can manufacture make some artificial defects on your sample surface. And next, which is more often cases, then you can do the cross-section on your sample. If you are interested in the interface, like for example, interface between the solid electrolyte and the anode, or the interface between the cathode materials, you can do the FIB cross-sectioning and to see what the contact, the physical contact between particles or between different layers. And another example is that you can do spin mill. So this is not a very common case, but right now I think it's gains more popularity in this field. So what's a spin mill? Which means you can tilt the sample to a grazing angle to the ion column, which means you can rotate the sample 36 degrees and with a gallium beam on. So by this way, you can etch the sample surface with a relatively large area. This is around 300 microns large. But by this way, you can spot away the surface contamination layer and make the grain structure visible to the beam. And other cases, for example, you can also do the circular mill, and like you can make a pillar or needle from a sample. This is generally used for some specific techniques like atom perm technique or like some synchrotron techniques, X-ray transmission techniques, because the thickness of sample, the tip is could be less than 200 nanometers, which makes the electron beam transparent or the X-ray transparent. And if you just practice more, you can also make some structure. Like for example, I would say it's a nano bunny on the tip. I just took maybe an hour, half minutes to make such a feature just for fun. Yeah. So about etching, there one question you have to ask. So what's the beam damage to the surface? You can etch the sample, of course, but there any beam damage to the surface of your sample during the etching process? So actually, this is a well-studied field. So let's look at the mechanism of lon-Matter interaction here. So for example, first, this is the gallium ions, the primary ions, which come to your sample surface. Since it's accelerated high voltage, it will penetrate into sample surface and generate some vacancies, also generate some recording atoms. So for example, here, they will knock off some lattice atoms and generate vacancies. And that's atoms which is knocked off the original lattice will also go to other lattice and will generate more vacancies. So even if you only have one gallium ion, it will cause a series of effects and a series of vacancies. And the question is that, do you know approximately how deep the range, the projected range of ions below the surface? So this will give you understanding how the beam damage or how deep the beam interacts with your sample surface. So James Ziegler, he's an expert in this field, and he's one of the pioneers starting in this topic. He also wrote a book about the stopping and the range of ions in matter. He designed a software actually. The name is SRIM, and short for the stopping and the range of ions in matter. And through this software, this is an open source software, so you can have access to it online. So through this software, you are able to simulate the dynamic process of the implantation process of ions into the target substrate. And this software, this algorithm is based on the Monte Carlo simulation. So it is a straightforward simulation. So for example, this is the example about how a gallium interacts with the target. For example, the substrate is a zirconia. It's a ceramic material. So if you have a 30 kV gallium beam and you shoot to your sample surface, what's the depth of the interaction volume and how much of that? So I will run one of the simulation here. One moment. Let me see if I can. Oh, the sound. Okay, so this is the interface of the software. It can input the parameter, the ions used for the gallium, and the ion energy 30 kV, and also the angle at which the beam should at your sample surface. And you can see this is the x-axis, the 15 nanometers. The 30 kV beam can easily penetrate into the zirconia ceramic, this ceramic materials up to around 20 nanometers. And you can see this, probably will see the red dots. That's the vacancy generated by the primary ions. And the blue dots are the vacancies generated by the recording ions. So for example, if you have, each time you have one, I saw a question here. Maybe I will talk to you later. So it's so I saw the question from Jeff. So it's nanometers. I mean, it's angstrom. So 500 angstrom corresponds to 50 nanometers. So the unit is correct. So, so for example, if you have one gallium ions, and it will trace the trace of the each ions, and during this trace, they will probably up to thousands vacancies generated just due to this one single atom. So this will be the implantation will be much more serious than you expect. So if you look at the distribution here, after some simulation, it give you a chart gram here, and the mean distribution shows that this 30 kV gallium items can penetrate up to around 15 nanometers. So through this software, you can not only simulate gallium beam, but you can not only simulate it, but you can also simulate more beams. Like almost every beam you can simulate. For example, this is a gallium beam simulated at 5 to 30 kV. At the same time, you can also simulate how the argon beam atoms penetrate into these ceramic materials. So at the same voltage you can see here, it looks like at the same voltage, argon beam can penetrate much deeper than the gallium beam. And if you look at the projected range, which is plotted, predicted by the software, and you will see at the same voltage, for example, 30 kV, the argon beam can actually the main distribution, the main projected range will be over 20 nanometers, and almost 2/3. I mean, except 150% of the gallium beam. So this kind of interesting thing that I was expecting the argon beam was better, but actually from the simulation, it looks like the damage or the implantation will be more serious than gallium beam. So that's why people will decrease the argon beam voltage to up to 5 volts. For example, if you have, we are going to have SEM mill on campus in this coming year. If you look at the parameter of the SEM mill, the high voltage they use for polished sample etching, they only control the argon voltage up to 5 kV. But even if at 5 kV, you still have the penetration depth around 5 nanometers. So this means that in this area, you will have argon atoms implanted in this layer. And probably, so it's hard to say will this affect other sense, but it's definitely good to keep in mind. It's not after etching or after polishing by argon or gallium beam, the surface layer definitely is or contaminated or implanted by these atoms. Another thing about the simulation you can see, during simulation, there is a sputtering yield. So this sputtering yield means that for example, let me start the video again. So the sputtering yield indicates how efficiency of this beam to sputter the sample surface. So during this process, the gallium ions not only penetrate into not only penetrate deep into the material, but also sputter atom at the surface. So the definition of the sputtering yield is that the how many sputtered atoms over how many implanted atoms. For example, number here. If you have, for example, here the total number sputtering yield 8, it means every one single gallium ions can generate around 8 vacancies at the surface. So also the oxygen, each element have its own values here, which means oxygen has higher value. It means that oxygen is easily depleted or be knocked off out of the lattice parameters. So which means if you have gallium beams image at the surface, you will definitely lose some oxygen atoms more easily compared to zirconia. And this kind of simulation results Okay, and move on. So there are some takeaways about this section about etching process. So we can say that almost any ions can cause implantation. It just depends on how deep and how much how much in your sample, in your target sample surface. And this simulation stream is good for the first order simulation on the ions matter interaction, because the first thing is that there are some assumption. First, this simulation, it runs on the 0 Kelvin. So which means it's a absolutely very cold temperature or cryo mode. So it also point out that even if you are doing cryo FIB, you are still seeing this implantation. The cryo FIB cannot remove any, cannot make the sample surface pristine. It can only reduce the damage due to the heat, due to the heat, or due to not good bad heat dissipation. And second thing that this simulation doesn't consider surface damage. So because if during the implantation simulation, the surface definitely will be changed. Like if you have some maybe amorphous region, maybe the phase change. This all will change the surface binding energy. And this surface, if the surface binding energy change, the penetration, the implantation will probably also change. So this several points we need to keep in mind when we run this simulation. So any questions so far I can answer? If not, we can continue here to the second feature, the deposition. So FIB can do local deposition. It is because then we can insert a nozzle into the chamber close to your sample surface. And this nozzle can flow precursors into your sample, to the area above your sample. And this precursor, basically just as gas molecules, will accumulate above your sample surface. Once this precursor interacted with the ion beam or electron beam, it will decompose into pure metals such as the platinum, tungsten, or carbon. And when you just keep flowing gas molecule precursor to the same area, it will just give a continuously deposition. If you stop flowing the gas and this ion beam, if it images surface, it will kind of sputtering away this material, and it will become an etching process. So the key is that if you can just continuously flowing the gas. Right now, the FIB has a pretty good control of the gas flowing, and this is not a big problem. So in the FIB, we can right now we definitely can deposit these several materials, and especially in the FIB on campus, we can deposit platinum, carbon, and tungsten. And in some other FIB in other areas, in other institutes, they can deposit some even more crazy materials, like some even some organic deposition. So that said that this deposition can be induced by either ion beam and an electron beam, which I will talk about in the next slide. What's the difference between this deposition? And another thing I would like to talk about that the FIB cannot only do 2D deposition. They can also do 3D deposition. For example, is how I say it, it's a toilet bowl. So you can see it's a 10 microns, around 10 micron scale, and you can make a CAD file, and then the FIB can do the deposition automatically, and to get the 3D structure done. So deposition. As I said, the electron beam and R beam can also induce this deposition. So what's the difference between them? So electron beam can induce like platinum or carbon deposition, but the deposition rate is pretty low. And the ion beam can deposit very fast at a very fast rate. But the drawbacks or the disadvantage is that during the deposition, ion beam will cause much high surface damage to the surface, because it's a heavy ions. During deposition, the sample is experiencing the surface imaging. So electron beam will cause less surface damage. So that's why people during the deposition will just deposit the electron beam induced deposition first, and then do the ion beam deposition to grow more thicker deposition. And since if we do the platinum deposition, it's relatively more conductive. So then people would like to make some contacts or deposit something post of the electrode, so then you can do the local measurement. But regarding the electrode material, we have to think about the conductivity of each deposit. So the conductivity are different, and actually, the deposits are not pure metal. If you look at the first column, it's the ion beam induced deposition. The pure platinum only maybe 40 or 50% of the materials. So the other parts components include carbon and oxygen, because the precursor have these elements, and the decomposition is not 100%. So that's why you always have some residues inside of the deposit. So the resistivity is definitely not a platinum resistivity, but it's not that bad. It's 10 to -3. It's definitely lower than most solid electrolyte or lithium-ion conductors. So the second column is the electron beam induced deposition. The platinum component has a less ratio, only around 20%. And so there's a higher ratio of the carbon and oxygen impurities or components in this deposit. So this means that definitely show that electron beam is not very efficient to do the deposition work. And also due to this carbon or oxygen components, the resistivity is relatively high. But people found that there are probably two options which can increase the electron beam deposition, because electron beam deposition can cause less surface damage. If we can also increase the conductivity of deposit, that would be definitely a good thing for local measurement. So people tried to do the post annealing after deposition, for example, 500 C per 1 hour. the resistivity will be reduced by 1 order of magnitude. And also, the second thing we can do is to just do a gallium implantation, which just simply use the ion beam to image this area. And you can just improve the conductivity by 2 order of magnitude, or reduce the resistivity by 2 order of magnitude. Another feature about the deposition is the halo effect. So what's a halo effect is then? You can do the definitely can do the deposition, but the precursor in the deposits sometimes will deposit out of the region. You can see the scales of the measurements here. If I only deposit the 6 microns size square, but the X-ray features, you can see there's some platinum deposits out of this square. And also, if in some paper, in this paper, they talk about the tungsten deposits, and this is the line of the tungsten line deposited by ion beam. You can see the halo effect away from this deposit line, and you can see this is the some deposition of tungsten, but gradually changed with the distance away from the tungsten wire. So this is how what we call the halo effect. So this definitely means this halo will definitely have some resistivity or conductivity, not as high as the deposit area, but it also has some conductivity. So we have to consider about that, because it may contaminate this may contaminate your sample, or can damage your electrical circuit, make it a short circuit because of the halo effect, especially when the 2 electrodes are very close to each other and you want to deposit some tungsten in this region. So the reason for causing this halo effect, then 2 things. The first, the gallium beam scattered to high angles during deposition, and this high angle scattered galliums will cause decomposition of the precursors out of the region. And secondly, that the scattering electrons caused during this deposition will also deposit the precursor in the region outside the pattern you want to, the desired pattern. So I just give one example in some in a paper Nature published last century, and they use this they use the FIB to deposit the full electrode wire to do a full probe measurement on this carbon nanotube. So from this paper, you can see they don't have any protection on this wire, and also there's no mask between this electrode, which means they just directly deposit platinum wires on top of that, tungsten wire on top of that. And the halo image, even if from this not very high quality image, you can see some halo contamination on the carbon tube. So until now, I think people just, it's weird that people underestimate the halo effect. And I'll still see some in high impact journals that just directly deposit platinum or tungsten of the electrodes when the samples or wires, nanowires, also experience the deposition without any protection and mask. So I would definitely propose that if you want to do the local, especially electrical measurement, you definitely need to protect either your sample or your substrate with a mask. For example, this is a platinum electrode, and there is a gap. If you want to measure some fiber or wire between this electrode, you can just lens the fiber there. And definitely to make a mask to protect this substrate before you do any platinum deposition. You can see the halo effect is quite crazy in this area. If you don't do any mask, then you make the substrate, insulating substrate, not insulating anymore, because this halo also has some conductivity. And this mask can be used some any other material which can be easily which can be pretty robust during deposition, but can be easily washed away or lifted off by some other solution. For example, here I just use the polymer coating with some gold, and this can be, it's not, so if you're coating some gold, it's not less conductive, and which good for the FIB imaging. But the polymer is thick enough and also can protect the substrate from gallium beam damage or implantation. So some takeaways from this section. We know that the deposits by FIB are not pure metals. They, at least half of them are carbon and oxygen because they are from the, because these are incomplete decomposition of precursors. And second thing I would like to point out, the halo effect cannot be ignored. And especially for the local electron measurement, we definitely need to protect our samples and substrate away from the deposition if we want to do any deposition work by FIB. So I think I'll give one special example here to show the halo effect sometimes is not entirely bad. For example, this is the lithium plating FIB work Jeff and I did last Saturday, and we deposited some around 100 nanometer thick platinum field on the LLCO, which is a lithium ionic conductor, and also you can see in this area there's some halo effect. The halo effect is pretty obvious. The film you have still have some precursor of platinum on that, but it's not continuous film. And I will show the video when we do the lithium plating. The lithium plating that we insert a probe touching this surface and do the lithium plating on the, and the counter electrode is lithium foils. You can see the lithium foil grows out of some fractured surface because the surface is not very flat. The platinum film get cracked at some points, and some lithium nanowires grow out of the surface. So I will just, you can see more and more. But if you look at this halo effect regions, something happened here. We have many lithium nanowires. We prefer to grow at these regions, even if this region has less conductivity and it's porous and it's not dense. But these areas have kind of looks like the more favorable nucleation sites for lithium plating. So yeah, so the halo effect maybe give us another more flexibility to do the surface treatment and to study the lithium plating in this field. And you can see the before lithium plating and after lithium plating. The continuous lithium film, dense film, there's no lithium plating, all dendrites, all cracks, even if only 100 nanometers thick. So all of lithium plating occurs around in the halo regions. So then last section will be the micron manipulation. I think this will be short sections. And so the micron manipulation is completed by using the Omni probe. So this is generally widely used to prepare TM samples. So we know that the FIB can do etching. You can prepare TM lambda, the pellets here, and remove this pellet to the TM grid. So there are a lot of questions about how to stick this TM pellet to the probe. So right now, I think I can summarize 3 types of methods that you can stick the sample to the probe and then transfer sample to the desired area. So first, the electrostatic force. For example, if your sample is a nanowire which only maybe tens of nanometers, you can just probe the manipulator close enough to the nanowire, and this nanowire would be a stick to this manipulator. And also, you can if you have some larger fiber or particles, the electrostatic force is not large enough to hold the sample. You can do the electron beam induced carbon deposition to do that, because the electron beam induced, you don't need there is no gallium beam, so the surface damage would be very small. There's no ion beam contamination. And also you do carbon deposition, which means you can do a post-annealing to remove the carbon after you transfer samples. And this is generally used very effective strategy to do the local electrical measurement. And also definitely the widely used strategy to use the ion beam is platinum deposition. But this is generally used for the TM sample preparation. You don't need to do any local electrical measurements. You don't have to worry about the beam deposition or beam contamination. So I would like to give another example here about external probes. So right now there is some commercial company develop many powerful probes inside the FIB, which can help you to, move to do the micron manipulation very fast and very efficient. For example, you are not using the one single probe. You are actually making a tweezer by the two probes. But this way, you can just hold the probe, hold the grab the sample and move to the area, for example, T lambda. You can do almost 12 minutes TM lambda lift outs within 12 minutes. And usually they will take around 1 hour or half an hour to do one transfer. So just a quick summary here. I think time is here. So the FIB can, the major, right now the major use of FIB is to prepare a sample, for TM, for Etching probe, for synchron studies. And I would say that there are some other functions that would be the powerful of uptake. The function is kind of underestimated. For example, we can use this Etching deposit function to do some micron nanofabrication, and even we can use this technique, this function to design and also manufacture some flexible platforms for local measurement and characterization, because the FIB is has the SEM chamber, SEM electron beam column. So which means you can do the electron beam imaging, EDX, EBSD at the same time to help to characterize the sample interface. So last, I would like to thank all my some subgroup and also thank to all of people in this group for the help and in the past year. And thank you. I would like to take any questions from here.
Thank you, Xin, for your wonderful tutorial on the FIB technique. If anyone has questions, feel free to unmute yourself and ask Xin. And meanwhile, if you have any comments, please feel free to leave them comments on the Google form.
Shane, I had a question.
Sure.
For the beam damage, there's a simulation that shows kind of how thick it should be. For people who make like TEM samples, can you generally see the beam damage in the TEM?
Yes.
Or is there another way to check for the beam damage before they do the TEM measurement?
So since the beam damage layer is is only nanometer scale, so it's hard for other technique to characterize this before NTM analysis. So right now, most of the techniques or the ways people do is to put the sample inside the TM column to look at the surface. And usually for gallium beam prepared samples, we will look at around 5 to 10 nanometers layer, which has different contrast to the interior part. And this part, this contrast, we think is due to the gallium implantation. This is a very common phenomenon in this FIB prepared samples. Even argon beam prepared sample, you can also see the surface layer.
Xin, I think in a SCM, can you just for gallium, I think you can pick it up with EDS, right?
Yes, you can do EDX. EDX can see the gallium, yes. But you don't know how thick it is, I mean, how deep it is. You're only looking at the surface.
Great, thank you.
Yeah.
Hey, Xin, can I ask a quick question?
Sure, definitely.
Yeah. So for the metal deposition sort of capability, either using the ion or the electron beam, what is the typical sharpness of the edge that you can fabricate using this? I mean, are we talking, tens of nanometers, or is it sharper than that? I'm trying to get a sense for how it compares to a typical like lift-off fabricated sort of metal step.
So are you doing the etching or deposition?
Deposition of metal, let's say, on some semiconductor, let's say.
So deposition. So so this is a very good point. If you want to do the very sharp deposition, I would recommend to use the, for example, use the ion beam. You definitely need to use a very high voltage and less current because this beam profile is very sharp and narrow. And for this deposition, I would say you can do definitely 100 nanometer with 100 nanometers features. You can never do that. But the thing is that if you do close, you have the halo effect, for example, here. I mean, here, if you can see this paper, this is last century, February, and this custom wire is 80 nanometer. They can do such high quality.
I see.
I would say the current, the FIB can even do much better than this.
I see. So,
but
so the thing feature, sorry, go ahead.
But the thing that you have to worry about the contamination between the two wires. And there are definitely some gallium or platinum in this region if you do not do any mask or protection.
Okay. Yeah, I guess, so the feature size is one thing. So I guess in this image, for example, it's 80 nanometers, which is the width of the wire. But so I'm guessing the sharpness of the edge is probably like 10 nanometer or something like that. Yeah. Is that fairly, okay, cool. All right, thanks.
The gallium probe, so the reason why use the gallium as the ion source, one of the major reasons the gallium beam can be confined to the probe size less than 10 nanometers.
I see, okay.
So definitely, so if less than 10 nanometers, you'll be able to do, at least do the fabrication of features up to 50 or 100 nanometers.
Okay,
I would say.
And just maybe a quick follow-up question. When maybe you said this and I missed it, but when you deposit something like platinum, let's say using the FIB, what is the grain size, or is it mostly amorphous? I mean, how does it compare to a typical, let's say, E-beam evaporated metal film?
You mean the grain size of the platinum?
Yeah.
So there is here, the chart shows the grain size.
Okay, I guess I did miss that.
So the ion beam induced deposition is around 6 to 80 nanometers. It was characterized by TEM.
Okay.
And electron beam induced deposition 3 to 5 nanometers.
Okay. Cool. Yeah. Thanks.
Sure.
Hey, seeing it's Will. I just want to tell everyone on a paper that I read maybe about 5 years ago. It was from the group of Johann Meyer, and they were actually doing STIXM, scanning transmission X-ray microscopy of a solid-state battery. I think the electrolyte, I want to say, was some sort of a lithium fluoride. I don't remember. It's not a very good one. And they actually developed a defect chemical model for gallium incorporation into the material. So I thought that was rather interesting. I forgot where the gallium goes. I think this was a Nature Communications paper about 2016, 2015-ish. So people have been thinking about gallium as a sort of substitution / point defect, specifically for solid-state batteries. So I think it could be something interesting to think about.
Yeah.
Are there any more questions? If not, thank you, Xin.